Sir. Here I am the room.
Okay.
Recording in progress.
So yesterday we were talking about hardware anemometer for measurement of velocity to predict flow rate. So we'll continue with that. So as I said, the hardware anemometer will have a cylindrical, very thin cylindrical wire made out of materials like tungsten or platinum and so on. And this wire actually forms part of a Wheatstone bridge circuit, as you would see subsequently. But when you have flow over a heated wire, there is going to be heat exchange between the cylindrical wire and the fluid. And we looked at the energy balance here by equating the heat that is dissipated by the hardware because of the electrical heating with the heat loss from the surface of the wire, which is because of the convection. And by equating the two, we arrived at this equation, which is known as the hardware anemometer equation. So here, A and B are constants. V is the velocity. N is again a constant, which is the exponent of V. And on the right-hand side, you have I, which is current that is flowing through the wire. The resistance of the wire. Resistance of the wire at a reference temperature could be the initial ambient temperature. And you have alpha. The alpha is the temperature coefficient that relates how resistance increases with temperature. And these are the parameters which actually affect the velocity. So this basic hardware anemometer is obtained from the energy balance, but the hardware probe can operate either in constant temperature mode, and this is called the constant temperature anemometer, CT anemometer. And then you have constant current anemometer or CC anemometer. So we're going to look at these two. In a constant temperature anemometer, so this is the Wheatstone bridge circuit that I was talking about. So you have R1, R3, and R4, which are standard resistors. And this branch here is formed by the hardware sensor, and this is R2, right? So initially, the circuit will be balanced, right? And when there is flow, you would see that the temperature of this wire is going to change because as compared to a quiescent state of the fluid, when the fluid starts moving, there is going to be convection, heat transfer from the wire to the fluid. Consequently, the temperature of the wire tend to fall down, right? But since it is a constant temperature anemometer, the circuit tries to maintain that temperature at a constant temperature. Now, in order to achieve that, something needs to change. So that is achieved by lowering the resistance. This shunt resistance here, RS, is basically lowered so that the current is increased. The current that passes through this hardware is increased. That means you have higher heat flux now being generated, which is convected into the fluid, maintaining the temperature constant. Otherwise, as compared to a initial quiescent state, when there is a flow, the temperature will not remain constant. So in order to keep the temperature constant, you have to increase the current that is flowing through the hot wire. So, and this is achieved by lowering the resistance here, RS. So if you look at heat dissipated by the hot wire, which is given as I square into R W, which is the resistance of the wire. Now, in this case, current is not held constant. Current has to be changed, right? Because the temperature is constant. So this I square RW can be written in terms of voltage. Okay. So I can be written as voltage, that is E divided by RW. So, and then RW is multiplied here. So you get E square over RW. This I square RW need to be substituted in the basic hot wire equation. So this is the basic hot wire equation that we derived here. So this I square RW need to be replaced by E square over RW. So when you substitute E square divided by RW for I square, you see that this resulting equation here, this voltage E is the only variable. In the right hand side, E is the only variable which is a function of V. All other parameters are basically constant. Okay. Resistance here, the reference temperature, resistance of the wire, because the temperature is held constant, the resistance of the wire will be held constant. So you can see that left hand side, this velocity is only a function of E. E is a variable here. So this is, you can write that, I mean, since everything else here is a constant, this you can divide by A and B, and anyway, these are going to be some other constant. Okay, so you can simplify this and write that E square is basically A plus B, which are new constants when you divide by R infinity alpha and multiply by RW into RW minus R infinity. And so you have E square equal to A plus B into V to the power N. Where this A, B are different than this A, B. Basically, this constant is observed in this A and B. So this voltage across the hot wire can be measured using a voltmeter. As you can see here, this voltmeter is actually measuring the voltage across the hot wire anemometer. Now, when there is no flow, when V is 0, let's say your output here is some E naught. Okay. In this equation, you can see that when velocity is 0, V is 0, so A will be equal to E naught square, right? So A is E naught square. So that means in this generic equation, you can write E square minus E naught square equal to B into V to the power N. Because at the limiting case, when V is 0, A will be E naught square. So this constant A has a value now, that is E naught square. That is the voltage at zero flow condition. So E square minus E naught square is B into V to the power N. And now, if you divide by E naught square, so you get E by E naught whole square minus 1 is B divided by E naught. I mean, this is again a constant. So you write B over E naught square into V to the power N. Now this, if you plot, you know the dependency of E with V, you get a nonlinear curve, right? As velocity increases, this equation gives you that your output voltage E basically increases in a nonlinear fashion. And as you know, nonlinear systems are not preferred, right? So you always prefer linear systems because for a linear system, if it is, if the values are obtained at some specific points, at other points you can always interpolate and extrapolate, right? So that for that reason, linear systems which are more predictable are preferred. So in the hardware, instead of using an equation like this, if you take logarithmic of the left hand side, so you have log of E by E naught. You take logarithmic of right hand side. So this is basically product of two things. So it will be log of B over E naught whole square plus log of V to the power n. Log of V to the power n will basically be n into log V. Now, if you plot this equation instead of this equation, and you have basically a log-log plot, you have E by E naught square minus 1 on a log-log plot in the x-axis. You have V in a log-log plot in the y-axis. You actually get a linear characteristics. Okay, so this is the linearized output of a hardware sensor. Now, for a given flow situation, you stick in your constant temperature hardware anemometer, and you can get an output. And for a given output, you can actually predict your corresponding value of velocity. Now that was constant temperature hardware anemometer, but hardware anemometer can also operate in a constant current mode. Now so this is the typical circuit. So you have the hardware probe here, and you are measuring a voltage across the hardware probe, and you have the source voltage here, source power. In addition to this hardware probe, you have a series resistance which is variable. You can vary this resistance. Now, when the current is constant, okay, the current is constant. So this is basically hardware probe. It is heated. So you have flow over the hardware probe. When the flow happens, the temperature goes down, right? And when the temperature goes down, the resistance would also go down. When the resistance would go down, the current in the circuit would change, right? But your aim is to keep the current constant. So in order to keep the current constant for a decreasing resistance here, you also need to come by varying this variable resistor such that the current comes back to its original value. Okay, the current remains constant. So this is basically the constant current anemometer. So again, you go down to your general equation, the general anemometer equation, which is A plus B into V to the power n is I square RW R infinite alpha divided by RW minus R infinity. Now in this case, the current is kept constant. So you can replace the resistance in terms of current and voltage. So in the previous case, the resistance was kept fixed. The resistance of the wire was kept fixed. So the current was changing. So you expressed in terms of voltage and resistance. Now in this case, the current is kept fixed. The resistance is varying. So you need to express in terms of voltage and current. So you adjust these terms in terms of voltage and current. And from here, you can actually, just adjust the terms. And you can say that when V is 0, you can have a value of A like the previous case. So E will be E naught. So that's why A is alpha E naught infinity divided by I into E naught minus infinity. And from here, you can actually solve for E infinity, which is A into E naught divided by A plus alpha E naught over I. This you can substitute here in infinity. So when you do, basically you have A plus B to the power n is, you get alpha over I E into this term, which is basically infinity, then E minus E infinity. This is E infinity. So if you walk through the math, I am not going to follow each and every step. This is relatively simpler to follow. Once you do that, eventually you can actually express your difference between the initial voltage minus the voltage at a particular V at a non-zero velocity of the medium in this form, which is A1 divided by 1 plus A2 into V to the power n. So here, this is the variable which depends on V. E naught is the voltage output in the circuit when V is 0. And yes, now this A1, A2 are basically constants. So that are expressed here. So A1 is K2B over K1A minus K3, and A2 is K1B divided by K1A minus K3. Again, this K1, K2, K3 are represented in terms of alpha, the constant A, E naught, and I. Because I is kept constant, right? It's a constant current anemometer. I is kept constant. E naught is the voltage at zero velocity. A is anyway a constant. So for these known parameters, you can evaluate K1, K2, K3, K4. And so you can know A1, A2. So you actually have the response. So now if you plot the output voltage E naught minus E with velocity, you get a trend something like this. Okay. So this is sort of a nonlinear trend which constant current anemometer exhibits. You can actually do calibration, do multiple measurements and then when you fit the experimental data against this theoretical equation, you can actually find out what is the value of constant A1, A2 through some kind of curve fitting. Okay. So this is for a particular, constant current mode hardware anemometer where the length of the wire is 100 micron and the resistance at room temperature, this R infinity, is taken as 2000 ohm. So this is kind of a typical curve that you see. And this shows you that as voltage is very high, this output actually saturates. So that can give you sort of, the operating range of voltage that one can measure using this kind of constant current anemometer. Right. So now this constant current anemometer can be used to measure steady velocity, where the velocity is not changing with time. But excuse me. But it can also be used for
Someone
measuring.
unmuted.
Yeah, can you please mute your thing? All of you, please mute your mic.
Arjun Jagakumar, can you mute it?
Left. Arjun Jagakumar.
Thank you. I think now it has settled. So what I was saying is that hardware anemometer not only can be used for measuring steady velocity, these instruments are sensitive enough to also measure fluctuating velocity. Like typically, if you have turbulent flows, as you know, laminar flows are orderly. That means at a given point, the flow may not vary that rapidly. Okay, it will vary. If it is varying, it will vary smoothly. But if you talk about turbulent flows are highly chaotic in nature, highly unpredictable. But if you have studied basics of turbulence, the turbulent velocities are actually decomposed into a mean component and a fluctuating component. Okay, even if at a particular point in the flow field the velocity is fluctuating, the fluctuations are decomposed into a mean component. That means something that is steady plus a fluctuating component. Now, hot air anemometer can not only measure the mean or the steady component or the time average component, it can also predict the fluctuating component. It is that sensitive. So when you try to measure fluctuating velocities, your time constant of the hot air anemometer becomes important. Okay. And when we talked about time constant, if you remember in the first order system, we had talked about time constant of a thermocouple, right? And this is similar to that. So a time constant of a hot air anemometer wire can be expressed in this form. Okay, density times speed of specific heat, rho into C, times volume of the wire divided by heat transfer coefficient into the surface area. Rho CV over H into S gives you the time constant of a hot air anemometer. Now, typically, these fluctuating components in a typical turbulent flow have a time scale of the order of microsecond. Okay, so that means the fluctuations happen of the order of every microsecond. So that means you need to have a hot air probe which has a time constant of that order. Okay, so typically, for turbulence measurement, we use hot air anemometers which have time constant of the order of 1 or 2 microseconds. Okay. Right. So that talks about the hot air anemometer, the fundamentals of hot air anemometer, how we derived the general anemometer equation, and then we talked about constant temperature anemometer, constant current anemometer, and we also said that these anemometers can be used for fluctuating velocity measurement, where the time constant of the anemometer becomes important, and they need to be small enough of the order of microsecond to measure fluctuating velocities like in turbulent flows. So now I will talk about another technique that can be used for velocity measurement and consequently flow measurement. The technique is known as Doppler velocimetry. Okay. So Doppler velocimetry is basically based on the Doppler effect. Okay. So it is a non-intrusive method because we are not really putting in any physical probe inside the flow field or a tube or channel or something. We are only exposing the fluid to sound wave. Okay. So the sound waves, they do not really, obstruct the flow field. So that is why these are non-intrusive methods. Okay. So the Doppler effects either use, electromagnetic waves or visible waves, infrared waves, or the ultrasound waves or microwaves. Okay. So let's say you have a tube in which some fluid is flowing. In the tube, inherently, there will be some particle, could be dust particle or could be some bubble. Okay. So this Doppler effect basically relies on those impurities that are present in the fluid. If there is no impurities present, these Doppler effects will not work unless you introduce some impurity into the system for measurement purpose, like you can introduce some particles or bubbles or whatever. So let's say there is a particle here, okay, and this particle is flowing. If you introduce this particle into the flow field, that is happening, let's say, inside a tube, we assume that this particle is flowing at the same velocity as good assumption. If the particles are small, they would tend to flow around the same velocity as that of the fluid itself. Okay. So if we can measure the velocity of the particle, or we can predict the velocity of the particle, we can say that you have the fluid velocity at that point is this much. So let's say we have a particle here, okay, and this particle is moving in this direction, in the northwise direction at velocity v. If we have an incident wave which is directed in a direction normal to the flow direction, right? This is the flow direction, this is the particle direction, and this is the wave direction. So we can place the transducer that is basically generating the electromagnetic wave or the sound wave by properly adjusting the location so that they are generating wave in a perpendicular direction. So this is the incident wave at some frequency f and some wavelength lambda. Now, when any wave falls on a particle, the particle, because of the finite size and a property difference between the particle and the fluid, it would scatter the wave. That is, fundamental to the wave theory. Okay, particle which is having different speed of wave and has a density difference and property difference as compared to the medium will scatter. So these scattered waves would be scattered in all directions, but if you have a transducer, if you have a detector at some angle theta, making an angle theta with the flow direction, you consider the scattered wave which is falling on the detector. And this scattered wave direction is again similar to the, can be adjusted by adjusting the receiver here, receiver or the detector. So let's say the scattered wave here is making an angle theta with the vertical, the flow direction. So when particle scatters, the frequency of this scattered wave will be different as compared to the incident wave. But the wavelength would not change. Okay, from wave theory, the wavelength of the scattered wave and the incident wave will be the same. So if you look at the incident wave, the wave velocity by definition is frequency times the wavelength. Or the frequency is basically the wave velocity divided by the wavelength. Now, when you have the scattered wave, the frequency of the scattered wave can be found by considering the net velocity along the scattered wave. So you have the scattered wave at going at a speed of c, but there is a component of this particle velocity along the direction of the scattered wave theta. So this component will be v cos theta. Now the fact that the particle is moving, the frequency is going to be different compared to had the particle been stationary. Okay. So this new frequency f dash is basically speed of sound c plus v cos theta divided by lambda. So there is a difference in the frequency between scattered wave and incident wave. And this is known as Doppler shift. Okay. So, I mean, you have one application of Doppler shift effect that you realize is when you are standing near, a platform and a train is approaching, making a sound, and you see that the frequency of the receiving of the signal continuously keeps on changing. Okay, the sound frequency that you observe when the train is observing far away compared to that is near are going to be very different.
Means I just done.
I know who is that fellow. Lakshmi Nurse.
Lakshmi
Yeah,
Jagameras.
I don't know.
So this Doppler shift is basically the difference in the frequency between the scattered and incident signal. So having learned that, if we have an incident wave which is coming and hitting at an angle theta I with a direction of flow velocity, in this case we said that the incident wave is orthogonal to the flow velocity. So there is no component of V in the direction of the incident wave. But let's say the incident wave is not making 90 degrees. The incident wave is making an angle theta I, and the scattered wave is making an angle theta S, right? And this is the particle, and which is moving at velocity V in this direction. So in this case, the Doppler shift is going to be from here, it will be C plus V cos theta I divided by lambda minus C plus V cos theta O divided by lambda. So the Doppler shift is going to be V by lambda cos theta S minus cos theta I. So this Doppler shift occurs only if particle has a non-zero velocity component along the direction of the traveling wave. Okay, and we also learned that the Doppler shift is proportional to the velocity of the particle. Okay, if the velocity of the particle is higher, that means the shift in the frequency between the incident and scattered is going to be different. And the Doppler shift follows a cosine distribution. Okay, and this would basically be 0 when theta becomes 90 degrees. Okay, so when cos theta S and cos theta I becomes equal, or theta S and theta I become 90 degrees, then this Doppler frequency becomes 0. So this principle is used to develop the ultrasonic velocimeter. First, I will talk about the construction of the ultrasonic velocimeter, and then we will talk about how it works. Okay. So typically, this is a ultrasonic velocimeter. The piezoelectric crystal is located here. This is basically the piezoelectric crystal, which is exposed to the flow. So flow may be in the right-hand side somewhere here. This piezoelectric crystal basically gives the electromagnetic incident signal. Okay. Inside, the cross section is this. The piezoelectric material is packed by a tungsten-loaded resin. The purpose of this resin is basically it sort of insulates any leakage of this energy towards the left. That means most of the energy is directed towards the right. And this is further, the energy is that leaking is attenuated by this observing material here. So only the energy is going in this direction. So this arrangement, having the loaded resin and the observing material, gives directionality to the incident wave. That is very important because we discussed that the direction of this incident wave is very important, right? Depending on that, the expression would change. So by insulating this way, we give directionality to the sound wave or the electromagnetic wave from left to right. And of course, you have a piezoelectric crystal, so you need to actuate So you can have some kind of electric connection. The power leads, connected to the positive and negative terminals of the piezoelectric crystal. And as you know, a piezoelectric crystal materials are such that when you apply electric field, they undergo deformation. So if you have an alternating high frequency signal, AC signal, which is applied, so they would deform very rapidly, right? And the deformation gives rise to compression of the fluid adjacent to the crystal. Thereby, it is basically giving a compression expansion wave, which is basically the electromagnetic wave, right? So this is basically the sound wave can be, or the electromagnetic wave can be generated using the piezoelectric crystal here in this way. So this structure is used to measure velocity inside a tube, for example. So you see, so you have a receiver, and you have a transmitter. So at the transmitter end, you apply electric field to the piezoelectric crystal, and it will send out a wave, right? Because of the deformation. At the receiver end, it works opposite. This same piezoelectric material, when the waves are falling on it, that means the material is undergoing deformation, it converts into some kind of electrical signal, right? So this is basically the receiver. So transmitter converts electrical signal to the sound or electromagnetic wave, and the receiver converts sound electromagnetic wave into electrical signal. So you have the receiver, which is giving away the incident wave, and there is some particle which is moving with the flow, and you are basically trying to measure the velocity at that point. So this transmitted wave hits the particle, and this particle scatters, and which is collected by the receiver here. And we said that if you know the frequency of the incident wave, frequency of the scattered wave, the difference between the two is related to the velocity, provided we know the wavelength of the wave that we are actually actuating. So you can see that we have a transmitted wave, which can be represented as the amplitude of the wave into a oscillatory component, which is typically a cosine function. So you write cos omega t. Omega is basically the frequency of the signal, and t is time, and this is the amplitude of the signal. So this is the transmitted wave. The scattered wave, as we said, the scattered wave would have a different frequency, right? So let that frequency be not omega, but omega plus omega d into t. So this omega d represents the Doppler shift, the change in the frequency of the scattered wave compared to the incident wave. So you would have omega plus, so this t should be actually outside the bracket. Okay, this is wrongly mentioned here. It should be omega plus omega d, and t will be multiplied outside the bracket, plus some phase lag. So the scattered wave will not only have a frequency shift, it will also have a phase shift of phi. Okay. So you have the transmitted signal, you have the scattered signal. Using signal, electronic circuit, you can multiply these two signals, right? So UT into UR, you can multiply the transmitted and reflected, the scattered signal. So UT into UR, which will be basically UT0, which is the amplitude of the transmitted wave, into UR0, which is the amplitude of the reflected scattered wave, into cos omega t into cos omega plus omega d into t plus phi. Now, this is like, if you remember trigonometry, this will be like cos A into cos B, which you can write as half of cos A plus B into cos A minus B. So you write S as half of these two terms are multiplied, but then this cos A into cos B, you write as cos A plus B, that is omega plus omega plus omega d, that will be 2 omega plus omega d into t plus phi. Then cos omega plus omega d plus phi minus omega, so it will only be omega d into t plus phi. So you can see that this way, this multiplied signal contains two different frequencies. There is a high frequency component. Typically, so this would be actually capital D. Okay, this D and this D are the same. This would be capital D. So typically, the incident frequency is very high as compared to the Doppler shift frequency. Okay, so omega is much greater than omega d. Okay, so the other thing to note here, so that means you essentially have a high frequency component here and a low frequency component here. Okay, this is high frequency component, this is low frequency component. And the other thing to learn here is that this signal S contains a high frequency component which is twice the input frequency. That means you have here 2 omega as compared to omega here in the input signal. Okay. So we learned these two things in the multiplied signal. So what we really do is we use a circuit, something like this. And the interest here is to determine the Doppler shift frequency, because Doppler shift frequency is theoretically related to the velocity using this formula that we have. Okay, this formula relates Doppler frequency to velocity. So we have to get this Doppler frequency, omega d. Okay, so in order to obtain the Doppler shift frequency from this signal that you get, you need to get rid of this incident signal omega. Okay, so this input frequency is basically removed by extracting the input frequency through a process called demodulation and passing this signal through a low pass filter. Because the Doppler frequency is much smaller. That means if you have a low pass filter, all the high end signals are removed. So demodulation basically segregates the frequencies, and the low pass filter will basically truncate the higher frequencies, only preserve the lower frequencies, which are the Doppler shift frequencies. So this Doppler frequency is of the order of 20 to 20,000 hertz. Okay. Whereas the transmitted frequency will be about 100 kilohertz. Okay, so this is about 20 to 20 kilohertz, but the transmitted frequency will be 1 order of magnitude higher. Okay, it will be in hundreds of hertz. So there is a very stark difference in terms of frequency. So what you do is basically you have an oscillator. Oscillator is basically this PJT transducer. Okay, PJT crystal which oscillates and gives the waves. So these waves get transmitted into the fluid. And you have basically some dust or impurity in the fluid which scatters signal. The scattered signal is basically received by a detector. Okay. And this detected signal is then amplified using an RF amplifier. This amplified signal would look something like this. you can see that it has a low frequency component like this and a high frequency component like this. Okay. So you need a demodulator that basically segregates this high frequency from the low frequency signal. And then it actually truncates all the high frequency signals and only leaves this low frequency signal. Okay. And that is basically the Doppler frequency that we are trying to measure. So you have a threshold that you set, okay, zero crossing detector. That means this Doppler frequency should not be, very close to zero. It should not be very small. It should be above a threshold value. And then you can actually multiply the signal. If it is, very small, you can, because you have now gotten rid of the high frequency signal, this you can multiply and make the amplitude, appreciable. And when you do that, then you can actually pass through a low pass filter just to remove any stray signal, which are well above the Doppler frequency range that you expect. And finally, you have the output. Okay. So the output basically gives you the Doppler shift frequency. And your control system also have this algorithm that knowing because in appropriate design, you know what is the angle of incidence. In this particular case, this is the flow velocity. So you know what is theta s here and the theta incident here and this theta scattered here. So these angles are known by design because of the placement of the receiver and your point of interrogation. So basically your theta s and theta I are known from the design. FD is known is obtained from the measurement. And the wavelength basically known because if you actuate the signal at certain frequency, what is the wavelength that is being generated. So, and then the only unknown then becomes V. So this can be included in the control system to finally give you the flow velocity. Okay. So that is how ultrasonic Doppler velocimeter works. Okay, so I will stop here, but if you have any question, we can discuss.
Recording stopped.
Sir, you had just mentioned it regarding the Doppler velocimetry measurement. If we don't have a loose particle or impurity, I would say, then hello, am I audible, sir?
Yeah, you're audible.
Then it will not be workable, right, sir?
Yeah, typically what you do, when we use some fluid, we say that, okay, is this fluid absolutely devoid of any impurity? If that is so, then this technique would not work because it relies on scattering of waves from some kind of particle, right? And if there is no particle, then what people do is they introduce some particle. If you have a measurement section, and then you introduce some particle that is non-interfering with the fluid or the process of interest, something like, bubbles of inert gases like nitrogen, which would not really, interfere with the process gas, or some inert particles, which would not really hamper the process, but it actually does the job for you, that it scatters the wave and it enables you to measure velocity in a non-intrusive manner.
Sir, I have a query over here is like whatever impurity or external particle is being injected in the flow. So we are assuming that the velocity of the particle will be along the flow and it should be almost similar, right, sir?
Yes.
But the particle will have some inertia. What I mean to say is it will have some finite mass. And if suppose the flow velocity is very low, and the mass of the particle is like you have told in the previous classes that a measurement can be intrusive or non-intrusive basis the qualitative thing inside.
Yeah.
So if the velocity of the flow is very low and the particle mass is little higher in that sense, so will that not be a erroneous, what I meant to say, measurement?
Yeah,
Or-
that is a very good point. So what people do is they use neutrally buoyant particles. That means particles which have similar density as that of the fluid. So they won't, I mean, even if the flow velocity is very low, they won't settle down. And typically the particles have to be very small. So talking about the fluid dynamics theory, if the particles are very small, they flow almost at the same velocity as the fluid molecules. Whereas if you use bigger particles, they would have a very different velocity as compared to the fluid. So that's why people use very small particles. They are easily dragged along with the fluid element. Almost have the same velocity as the fluid particles.
Thank you, sir. Thank you.
Typically of tens of microns to sub-millimeter size particles, depending on the flow scenario, are adequate for this kind of application.
Okay, sir.
Sir, in case of hot wire anemometer, you mentioned that we can measure this turbulent flow,
Yes.
and there will be some steady component, whereas there is some fluctuating component. So can you just elaborate a bit how the fluctuating components are being measured?
So see, the steady component would give rise to for example, let's talk about this constant temperature anemometer. So we are relying on the output voltage as a function of velocity, right? So the output signal will have a sort of steady mean value, but then there will also be an oscillatory component. Okay, so something similar to what you see here. You have a large high frequency component, and then almost a steady. It's like a low frequency signal. So here, the mean flow would have a low frequency component, which would have a almost stable value of output E. But then the high frequency component that comes from the fluctuating component of velocity, which will lead to a large fluctuation in the output voltage. So, I mean, electronic is much improved to capture that kind of signal, right? I mean, microsecond kind of thing they can always capture. But what is important is thermally, it has to be that quick. So that means the thermal capacitance has to be appropriate. These parameters have to be appropriate so that this time constant becomes really, really low. That means as soon as there is a perturbation in the velocity, it should appear in terms of change in the voltage. So that can happen only when the response time is very, very low. Right? We talked about when we talked about orders of system, first order system. Only when the response time is very low, it can do the dynamic measurements very well, right?
Yes, sir. Yes, understood.
Okay, so if no further question, then thank you, and we would meet on Monday. I think, I could finish this chapter on flow measurement on Monday, and then maybe we will look at some basics, or we can solve some questions from the quiz 2. as promised, to do that before we move ahead. Okay.
Hello, sir. Audible, sir.
Yeah.
Sir, coming Wednesday, IIT is working, sir.
Is there a holiday? I do not know.
No, sir. Before the Diwali, sir. That is why I'm asking.
Okay. This is
So
the
people
day.
will travel.
When is Diwali? Diwali is 31st, right?
Thursday,
yes, sir.
Okay.
Thursday.
So, okay. I mean, if you think that most of you will be traveling, then we would not have a class on 30th.
Okay. Thank you, sir.
Okay.
Right, sir.
Thank you.
Thank you.
Thank you, sir.
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 Thank you, sir.